Okay, let's jump right in. The paper today is Diffusion Language Models are super data learners. And wow, this one really uh, throws a bit of a wrench into how we've been thinking about scaling LLMs. For the quick overview, the big problem isn't compute anymore. It's finding enough unique, high-quality data. That's becoming the real bottleneck.
Exactly. And the core finding here, the big takeaway, is this crossover. When you run out of that unique data and have to start repeating data sets, diffusion language models, DLMs, consistently start outperforming autoregressive models, AR models, of the same size.
Consistently and universally, they say.
Yep. Universal crossover.
And it's not a small difference either. They're talking about a data efficiency gain of roughly 3x.
Which is huge, right? It means a DLM might only need, say, a third of the unique data to get to where an AR model is performance-wise.
They gave a pretty stark example, too. A 1 billion parameter DLM trained on just 1 billion tokens.
Which means, yeah, repeating that data like 480 times.
Yeah.
Crazy repetition.
Right. And it still hit 56% on HelloSwag, 33% on MMLU. An AR model just, well, it wouldn't get close under that kind of data pressure.
No way.
And the reasons they point to, it's a mix. This any order modeling, super dense compute from the denoising steps, and built-in noise acting like augmentation.
It's like a fundamentally different way to learn from the data you have.
Okay, so that's the snapshot. Let's dig deeper. For years, the standard playbook for LLMs has been autoregressive, left-to-right prediction. Why was that the go-to, and what's shifted?
Well, AR models took off because they're incredibly efficient with compute, relatively speaking. Back when we had, seemingly endless streams of pretty good web data, the game was maximizing signal per FLOP. AR is great for that.
So just read through once, predict the next word, move on. Simple.
Simple and efficient. But now, compute keeps scaling, but getting new, good text data. That's the hard part. We're hitting the limits of unique data, so we have to repeat data.
So the question changes. It's not how fast can I process data, but how much can I squeeze out of the data I already have?
Precisely. And that's where this paper argues DLMs, with their masked or absorbing diffusion approach, really shine.
Okay, talk about that theoretical edge. Why are DLMs supposedly better at, rereading the same book over and over?
The core difference is the modeling objective. AR models have this strict left-to-right causal bias. They predict the next token based only on past tokens. Great for generation, sure.
But maybe not optimal for deep understanding.
Right, especially for things that aren't strictly sequential, like code structure, or maybe even understanding complex arguments. DLMs break that mold. They use bidirectional attention, they see corrupted versions of the whole sequence, and try to predict the original tokens.
Any order modeling, they call it, like filling in a crossword puzzle instead of just reading left to right.
Exactly. Filling one word helps you with all the others simultaneously. It's about understanding the relationships across the whole sequence, not just the preceding history.
So it's constantly refining its understanding of the entire context.
Yeah, and the objective itself is repetition. You have to average the loss over many different ways the sequence could be corrupted or masked. So seeing the data again, but masked differently, so that's not just repetition, it's synergistic. It helps the model learn deeper patterns.
It makes the repetition part of the learning process, not just a brute force thing.
Precisely. Which unlocks things like modifying context on the fly or generating multiple tokens at once, things AR struggles with.
Okay, let's get into the empirical side, the intelligence crossover. We know the theory, we heard the 3x claim. How did they actually demonstrate this crossover in practice?
They set up experiments where they fixed the total compute, like, say, the model sees 96 billion tokens total during training.
Okay, fixed compute budget.
Right. But then they varied how much unique data was in that budget.
Yeah.
So maybe you have 96 billion unique tokens, see each one once. Or maybe you only have 500 million unique tokens.
Meaning you repeat that small data set almost 200 times to hit the 96 billion total.
Exactly. And they tracked performance across these scenarios.
And the result?
The crossover was clear as day. Once you hit that point where repetition becomes heavy, the DLM performance curve just keeps climbing while the AR curve flattens out, it saturates. The DLM overtakes it.
That 3x number again, where did that specific figure come from?
That was from a specific comparison, yeah. A 1B parameter DLM trained on just 0.5 billion unique tokens performed as well as an AR model needed 1.5 billion unique tokens to reach. So 3 times the unique data for the AR model to match the DLM.
That's a compelling number when unique data is your constraint. Okay, if this crossover always happens eventually, the key practical question is when. What makes it happen sooner or later?
They looked at 3 main factors. First, Pretty obviously the unique data budget. The more unique data you have, the longer the AR model can keep up, so the crossover gets pushed later in training.
Makes sense. What else?
Data quality, this is interesting. Higher quality data also push the crossover later. It seems AR models benefit more, or perhaps are more sensitive to, really clean, high-signal data. They hold their edge longer if the data is pristine.
Okay, so more data and better data delay the inevitable win for DLMs. What about model size? This is where it gets weird, right?
Yeah, this is where standard scaling intuition kind of breaks down, especially for AR in this data-scarce regime. Larger model size actually makes the crossover happen earlier.
Wait, hang on. Bigger models usually mean better performance. You're saying here, for AR models, going from 1 billion to 8 billion parameters when data is limited makes them hit the wall sooner.
That's what the results show. Think about it. The bigger AR model has more capacity to just memorize the limited unique data faster. Its hypothesis space, because of that causal structure, is relatively limited, just the sequence length L different prefixes.
So it overfits the small unique data set much more quickly.
Exactly. It saturates because it runs out of new patterns to learn from the repeated data within its restricted view. DLMs, though, keep benefiting from scale because their hypothesis space is massive.
Right.
They're averaging over all possible ways to corrupt the sequence that's like 2 to the power of L variations. A bigger DLM can actually make better use of exploring that huge, noisy space generated by the repetitions, and it doesn't saturate nearly as fast.
Ah, okay. That combinatorial explosion in the DLM's view makes it much more robust to just seeing the same stuff over and over. Very interesting. So DLMs are data efficient, but there's no free lunch. Let's talk compute cost. They call DLMs super dense. What does that mean in terms of FLOPs?
It means they need a lot more computation, both for training and for inference. The main reason is that iterative denoising process.
The multiple steps to generate output.
Right. An AR model generates a token, adds it to the KV cache, predicts the next one. Pretty streamlined. A DLM might need to run its network multiple times, refining the output over several diffusion steps, often using bidirectional attention each time. That adds up to way more FLOPs per generated token.
That's the trade-off. Pay more in compute to get more out of your data.
That's the core idea.
They also looked at sparsity mixture of experts, MOE, in this context. Trained dense and MOE models with only 1 billion unique tokens, repeated for 96 epochs. How did sparsity change things?
Well, first off, DLMs still beat AR models, whether dense or sparse. That baseline advantage held. But the effect of sparsity was different.
How so for AR?
For AR models in this data-starved situation, making them sparse, like an 8B model with one active expert, 8B1A MOE, actually made performance worse than even the smaller, dense AR model. Scaling up with sparsity actively hurt when data was repeated so much.
So sparsity, which usually helps scale efficiently, backfired here for AR.
It seems so. Maybe the routing struggles with highly redundant input, or it just accelerates the overfitting. Whatever the reason, sparse AR did poorly in this specific high repetition setup.
And for DLMs, how did sparse DLMs fare?
The sparse DLM, the 8B1A MOE, generally performs somewhere between the 8B dense DLM and the 1B dense DLM. They still showed benefits from scaling, even with sparsity. It reinforces that DLMs handle the repetition better fundamentally.
Okay, so the architecture matters. Let's try and pin down why DLMs have this edge. Is it just the noise acting as data augmentation? Or is it deeper? They did some tests adding noise to AR models, right?
Yeah, this was important to check if you could just, fix AR by making it noisier.
Yeah.
They tried adding input noise, basically randomly masking some input tokens for the AR model.
Did that help the AR model?
It did, yeah. Adding noise helped the AR model perform better under data scarcity compared to a clean baseline. It suggests augmentation is useful when overfitting clean data.
But not enough to catch the DLM.
Nowhere close. The noisy AR model still saturated much faster and performed significantly worse than the DLM.
What about adding parameter noise, like dropout?
Similar story. Helped a bit, reduced overfitting maybe, but didn't close that fundamental gap with the DLM.
So the conclusion is?
The advantage isn't just about noise or augmentation. It really seems to be the combination of all three things. One, the any-order modeling that breaks the causal chain. Two, the super-dense compute allowing thorough processing. And three, the built-in, richer Monte Carlo augmentation from the diffusion process itself.
And crucially, that the DLM objective needs repetition to work properly.
Exactly. Repetition isn't necessary evil like it is for AR. It's part of the design.
Makes sense. Now, was this just seen in smaller academic setups, or did they test it at a larger scale?
They did a large-scale validation run, specifically on code generation, which is a good real-world test case, high-quality data. but often limited in quantity compared to general text.
What were the specs?
A 1.7 billion parameter DLM trained on 10 billion unique Python tokens. That's a decent size for a specialized data set. They ran it for 150 epochs, about 1.5 trillion total tokens processed.
And did the crossover hold? Did the data efficiency show up?
Oh yeah, big time. The crossover happened relatively early, and the final DLM coder performed on par with state-of-the-art AR code models that were trained on trillions of unique tokens.
Wow, so orders of magnitude less unique data for the DLM to reach parity?
Exactly. It really validates the core finding at a practical scale.
Okay, before we wrap up with implications, there's this critical point in Section 5 about diagnostics, the validation loss, the NLL. It can be misleading.
Hugely misleading, yeah. This is super important for anyone training these models. We're all trained to watch the validation loss. If it starts going up, that means overfitting, right? Time to stop training or lower the learning rate.
Standard practice.
But this paper shows that, especially when you're deep into data repetition, a rising validation NLL does not necessarily mean your model is getting worse at downstream tasks.
How can that be? Why does the loss go up if the model is still getting better?
It's about the difference between absolute NLL and the difference in NLL between the right answer and the wrong answers, what they call delta-REML. Think of it like this. As you repeat data, the model gets more confident about everything it sees frequently. So the raw probability, or log likelihood, it assigns to both the correct and incorrect options might go up. This makes the average NLL look worse.
Because it's becoming overconfident overall.
Right. But what matters for accuracy on, say, a multiple choice task is whether the model is more confident in the right answer than the wrong ones. That difference in confidence, the delta-REML or the discriminative margin, can actually keep increasing even while the absolute NLL is rising.
So the model is getting better at telling the right answer apart from the wrong ones, even if its raw confidence scores are drifting upwards.
Exactly. Its discrimination improves. DLMs eventually overfit too, but this effect seems much more pronounced, and they resist actual performance degradation for much longer because of that huge hypothesis space we talked about.
That's a major caveat for interpreting training curves. It really shifts how you might evaluate progress. So let's summarize the big picture trade-off here.
Okay. AR models are the current champs because they are brilliantly optimized for current hardware. Great use of GPUs, efficient sequential processing, high signal per FL up when data is plentiful. They found a really good local optimum.
And DLMs are making a different bet.
Totally different bet. They're saying, let's intentionally sacrifice some of that computational elegance. Let's use more FLOPs. Let's do things iteratively. Let's embrace bidirectional context. Why? To get way more out of each precious, unique data point.
P-compute now to avoid hitting the data wall later.
That's the essence of it. So the forecast. If you believe high-quality, unique data will remain the primary bottleneck,
which seems increasingly likely,
then DLMs look like a very compelling path forward for pushing the state-of-the-art in terms of capability per unique token.
But there are practical hurdles for people wanting to deploy these today, right?
Oh, absolutely. The inference side is the big one. AR models have highly optimized inference pipelines, things like KV caching are mature. DLMs, with their iterative generation, are just inherently more compute-intensive at inference time, and the software stack isn't as developed yet.
So better potential capability down the line, but slower or more costly inference right now.
That's the trade-off facing engineers today.
Okay, that brings us to a final thought, building directly on that NLL insight. If rising validation loss doesn't always mean worse performance, and what really matters is the discriminative gap, and delta LLL, does that change how we should be training models?
It's a provocative question, isn't it?
Yeah. Are we maybe too obsessed with minimizing that absolute NLL score on our validation sets? Could that focus actually be holding us back from developing models that are ultimately better at discriminating correct information, even if they seem less well calibrated by traditional NLL metrics?
Should the goal be maximizing the margin, not just minimizing the loss? It definitely gives you something to think about for your next big training run, especially if data is tight.